How y'all doing today? This is a really cool venue. Kind of interesting looking up at everyone. But yep, my name is David. I am a software engineer. I do TypeScript, and it's always a great day when I get to get up here and talk about my personal favorite feature of TypeScript, conditional types. We only got 20 minutes today, and I plan on using every second of that. So without further ado, let's go ahead and get into things. So what are we going to be talking about today? Today we're going to start with a broad overview of conditional types, understanding what extends means, which is really just looking at the syntax of conditional types. We're going to get into this big fancy statement called the distributivity of conditional types. Really all that is just looking at how conditional types behave with type unions. And from there we're going to explore and infer a little bit before getting into pros and cons and what you should consider using them. Cool. So with that out of the way, let's go ahead and jump right in and talk about conditional types. At kind of a basic level, conditional types in TypeScript enable us to choose types based on a comparison or condition, very similarly to how conditional statements do in programming. And kind of a nice thing that TypeScript keeps with as we're looking at some of these more like obscure features like conditional types, they share a similar syntax with JavaScript as well. So when we're actually looking at conditional types, they follow a very ternary-like syntax, which is that question mark and the colon up there. And how we actually check for our conditions is we look if some type extends some shape. Oh, that's going to be annoying. New computer, sorry if that occasionally pops up. But we're going to check if some type extends some shape. If it does, we're going to walk down the truthy path, so to speak. Otherwise, we're going to move to the falsy path. So looking at a little bit more of a practical example, although still a little simple and contrived, we can take a peek at this hasID utility type. It is a generic type that accepts entity as a type argument, and all it does is it checks if entity extends ID of type string, meaning, hey, does whatever pass in here have an ID of string on it? If it does, it's going to spit out true. Otherwise, it's going to spit out false. So if we were to pass in our user type right above here, it would spit out true because, as we can see, user has ID of type string. Cool. So at its core, like this is all it is. Very simple, kind of interesting, might not feel super useful quite yet, but fairly straightforward. Where conditional types start to get interesting is if we look at what happens when we start combining them with our type unions. This is where we're going to start getting into that big D word at the beginning, distributivity of conditional types. If any of you have a math background and are seeing distributivity, it's the exact same word. If you don't have a math background, don't worry about it. We'll talk about it a little more. But before we get into it a little bit, in case you're not familiar with what a union type is, a union type is a TypeScript type that you can hold multiple specified types. So up there we have that type pet, where we can see it's going to be a dog or a cat or a fish and so on. It doesn't need to just be string literals up there. We could use objects, booleans, numbers, whatever our hearts desire. So what happens when we give our conditional types a type union? Well, as it turns out, that condition is going to be distributed to each member of our union. So up on the screen here, we have the definition of non-nullable. Has everyone here used non-nullable before? Hands? Yep, one thumbs up. One hand over there. Cool. If you haven't used it, don't worry. It is a utility type provided by TypeScript out of the box. And this is its definition, where it's basically checking, does T extend null or undefined? If it does, it's going to return never. Otherwise, it's going to return whatever it passes in. Now, if anyone's out there in the audience fact-checking me right now, this is actually an old definition of non-nullable. In TypeScript 5, they replaced it with kind of an interesting intersection type, which we don't have time to talk about, but yeah. I always like non-nullable because I think it's a very accessible example for looking at the distributivity of conditional types. So how does it work? When you give this non-nullable a type union and it has string or number in it, it's going to be removed. So what I want to do is I kind of want to walk through a mental model of how we can build up or kind of imagine how non-nullable is doing this with the distributivity of conditional types used. So kind of starting from the top, we have our string or number set equal to non-nullable, maybe string or number. We know non-nullable is a conditional type. We also know maybe string or number is a type union, and we know that conditional types distribute to each member of that union. So one of the ways we could think about this is rewriting it as string or number is going to be equal to non-nullable string, non-nullable number, or non-nullable undefined or null. From there, we can go ahead and strip back some of our generic syntax and replace it with the ternaries that non-nullable type alias is hiding. This is also where I stopped reading the slide because no one wants to hear me try to suffer my way through a big old ternary like that. It sounds ridiculous. I tried it once, don't do it again. So yeah, if we were to go ahead and evaluate each of these ternaries, we'd be left with a rather interesting looking type union. We have our string or number or never or never. Unfortunately, we don't have time today to get into never and why it behaves like this, but anytime you see never in a type union, you can get rid of it. How you can read this union up there is a string or a number or something that's never going to happen or something that's never going to happen. So since it's never going to happen, we go ahead and kick it out of the type union, and that's what ultimately leaves us with our string or number. So this isn't exactly how TypeScript does things under the hood. It's just more of a mental model to further grasp the idea of distributing over that type union. Cool. So last thing I want to talk about with conditional types before we jump into pro cons and when you should use them is infer. So it's always exciting when you get access to a new keyword, and conditional types in TypeScript give us a new one itself called infer. And infer is a little weird, but essentially what it is you telling TypeScript, hey, you know, if it matches this pattern or extends this shape, you should be able to infer a little bit more about it. And once you figure that out, give me a variable so I can refer to it. And that's exactly how it works. We're going to look at a couple of examples using infer. It's one of those things where it's super hard to define and describe. I've scoured the internet a bunch of places looking for it, talked to a lot of people, but I think a couple examples illustrate it best. So, starting with our type unwrapped promise, we can see it is a conditional type where we are checking if value extends a promise. Basically, is whatever we pass in a promise. And if it is, we are asking TypeScript to go ahead and infer what it unwraps to or what it resolves to. And once it figures it out, we're going to be able to refer to it by this unwrapped variable inside of our truthy path itself. So otherwise, if it doesn't match the pattern, we don't care, kicking it out with never. So if we were to pass in a promise that resolves to type number into our unwrapped promise type, we would get number out. Probably not the best way to get number, but you could do it this way if you really wanted to. Sweet. The generic syntax can be a little weird to read, so I also like to look at it with template literal types, and I think this is a lot more accessible, mainly because it's just like sentences. So say we have two statements. The first is, I will keep you here all night, and the amended is, I will keep you here till 4. So if we wanted to figure out how long we are going to be kept somewhere, we can use conditional types and infer to go ahead and deduce that from our types. We would create a generic type that accepts some string, and we would check if string extends I will keep you here space, basically saying, hey, does this sentence start with this? And if it does, we ask TypeScript to infer the rest of the sentence. So once it infers that, we refer to it down here in our truthy path. Otherwise, we spit out never. So in the case of our two sentences we talked about before, I will keep you here all night, spits out all night, and the other one till 4. Sweet. So that's the broad overview of conditional types. Kind of the main three things here are they behave just like ternary in JavaScript or TypeScript. They distribute over unions, and they give you access to a new keyword called infer. Something to mention about infer, the variable that you infer can only be used in the truthy path of your conditional types. That's because if it doesn't match the pattern, TypeScript cannot infer anything about it. And on top of that, infer is a conditional types feature, not a TypeScript feature. So you have to use it within that extends clause of your conditional types. Sweet. So with that out of the way, let's talk about some of the benefits that you can get out of using conditional types. It's so cool having this big screen here. Cool. And kind of the high-level breakdown of what the benefits of conditional types are is they produce a lot more intuitive DevX. A lot of the times when you're using conditional types, you're going to move beyond the kind of necessary and sufficient typing to something that's a lot more interesting to use for developers. And there's a couple things in there that really make this possible. The first is dynamic type manipulation, which is really just saying that your type logic adjusts dynamically. Up on the board, we have a very simple example of this, a little contrived. You probably wouldn't do this. But you can see here we have an API response type that has a type argument for the data because whatever comes back, we want to be able to type using that type argument. And on top of that, we have a multiple type argument to denote whether or not we want it to be an array of that or just a single instance of it. Again, little contrived because you could just use tdata to pass in the array, but it illustrates some of the cool things you could do with conditional types. On top of that, it also gives you a lot more flexible inference. So up here on the board, we have this declared function called getAnimalSound. We can see it's looking to accept an animal, which in our case is just going to be a cow or a dog or a cat. And whatever we pass in is going to determine what we return. So you can see here, if we go ahead and pass in a cow, we're going to spit out moo. If we pass in a dog, woof. And if we didn't pass in a cat or a dog, we pass in a cat, which means we're getting out meow. So you get a lot of cool things out of conditional types. If you were to drop all of these in an IDE, you would see that const moo is moo, woof, and meow are both the same as well. On top of that, you also get a lot more sophisticated utility types. So again, going back to the utility types that TypeScript provides, a lot of the really powerful ones, exclude, extract, return types, and parameters, those are all powered by conditional types. And infer on top of that inside of return type and parameters. So a lot of these things are only doable with conditional types, so that's super awesome. Sweet. So where are we at? Okay. So with that, we can kind of get into some of the complications or the cons of using conditional types. And where we can break this down is really complexity. Dealing with conditional types can be a pain in the butt. So getting into our first example here, I don't know if you guys are on TypeScript Twitter, but back when I was making this presentation, this type was making its rounds, and this is a bunch of nested conditional types. It looks like we got some recursion going on down here all over the place. Very complex to read for just a type. Can anyone summarize this in like a sentence? Silence? Yeah, same. So yeah, that's Adam Rakis's type on Twitter. I think he was bragging about working together with someone, getting it working, and it turns out that even this had a couple issues with it. And my mic died. Oh, it's back. Okay, I was worried I was gonna have to scream. Cool. On top of there also are limitations to what inference allows you to figure out with your conditional types. Going back to our idea of that getAnimalSound function, I've gone ahead and eliminated cow just to go ahead and make this a little smaller. But we have the exact same setup where we're just looking at dog and cat. And we didn't deal with the implementation last time. If we were to go in and try to implement it, this function should be really simple, right? We just check if whatever was passed in was a dog. If it's a dog, return woof, otherwise meow. The issue is that how inference is currently, you're gonna get a type error if you do this, and it's gonna say, hey, you know, woof is not assignable to our conditional type, which we have being returned from our getAnimalSound function. There's not a great way to get around this, so you do end up having to assert it at some level or another. And on top of that, we also have the maintainability issues. We've seen some of the complexities, we've seen the error messages that can arise from it, and we also know this is kind of a more obscure feature of TypeScript. So these three things put together makes it hard to introduce with confidence into your code base. Sweet. So on that sour note, so when should I actually use these? I'm gonna trip over a cord. When should I use these? And just like everything else in programming, it depends. Thank you guys for coming. I'll see you guys tomorrow. But no, it depends. And while I would like to wrap this up right here, I'm not gonna do that. Instead, I wanna kind of break up how our day-to-day development lives generally look. Online and within the industry, there's been a nice little split that I think helps articulate where we have more complex type logic. You have your app level code and your library level code. So with that in mind, I'm gonna answer when you should use conditional types in respect to those two ideas. Cool. Starting with your application level code, this is your day-to-day. I'm building UI, I'm getting features out the door, providing stakeholder value. When you're writing that kind of code, you're gonna very rarely need conditional types. They're kind of complicated, they produce weird error messages, and you don't need the benefits that they provide. If you do find yourself needing them, chances are a TypeScript utility type is all you're gonna need, and chances are you're also in your utilities folder or your service layer or anywhere else where your more complex and more generic logic resides. So kind of an example of that, we have some use recipe hook up there that use awaited and return type, both conditional types, or we're extracting from our event type, or extracting from our events everywhere where the type is add. One kind of cool thing about conditional types is it does let you write your logic very similarly to how you write your types. I kind of like that. Some people might not. Take it or leave it as you will. But in application code, you're going to very rarely reach for conditional types. Which brings us down to our library level code. There are a bunch of different reasons that you would want to reach for conditional types when you're writing library code. My three biggest are type-safe constraints, anytime you need to do some sort of advanced type mapping, and type distillation. So type-safe constraints, which is basically we can enforce and validate constraints at type time. So up on here, you can pretend like we're creating some library that creates a bunch of schemas, and we have this create attribute function. We also see that it accepts a primary and a required Boolean just to kind of figure out what we're allowed to add into this schema. And if we have primary set to true, we really don't want to allow required to be false. If it's our primary thing, we need it there. So with conditional types, we can go ahead and enforce that. And all that would look like is we have our create attribute function, a little bit of plumbing to get out of the way, that accepts primary as a type argument. It extends Boolean because it's either true or false. And we go ahead and pass that into our attribute config. Inside the attribute config, that primary type argument ends up on the primary key, and the required one can be derived with a conditional type dependent on primary. So if primary extends true, we are forcing it to be true, otherwise we don't really care if it's required or not, so we're going to return out Boolean. So kind of cool that we can enforce type-safe constraints we can enforce these constraints at a type level. Cool. On top of that, you can do advanced type mapping with conditional types. We saw it a little bit in the tweet from Adam earlier, but with conditional types and being able to choose different paths, we also have the ability to recurse through our types. So kind of an interesting example of this is we have a get path segments function, which we can imagine is going to split up a path and return out an array to our users. And rather than just typing it as a string, we can actually use conditional types to create a union of our path segments. So what that would look like is you have your function, again, a little bit of plumbing where we make our type argument path, and we are returning out, returning out the split of that path. I think I'm going to make it. Yeah. So what that looks like, I could talk for hours on this type, but we're not gonna, is basically what we are going to do is we are going to take that path, we are going to figure out if there is a slash in there. If there is, we're going to take what's before the path, store it away in an array, and go ahead and recurse and split the rest of the path, building up an array of path segments up until we no longer match this condition, in which case we are going to return out all of the path segments from that array as a type union using this cool little array trick with index access types. Cool. On top of that, there's also type distillation, which is essentially breaking unions down into smaller subsets and refining them. So sticking with our split path example, let's say we wanted to only grab the path parameters out of that union. We can use conditional types and infer to go ahead and do this just by checking if t extends colon, which is just saying, does the string start with a colon? If it does, infer the parameters, and let me refer to it as p, and spit out p, otherwise never. If we were to do this and pass in the split path we just had, we would get id and org out, because id and org are the only ones that start with a colon. Sweet. It's got about a minute left, perfect timing. As a quick wrap-up, conditional types produce an intuitive and effective DevX, but they come at the cost of complications within your code base. In general, if you're writing application-level code, you're really not going to use them all that often, but within your library code, you're really going to be primarily using it for type refinement. So that's all we have time for today. I'd love to talk about any of the stuff you guys have questions about. Pretty sure that goes to my LinkedIn. Don't hold me to that. I forget where it goes sometimes. And all the slides are live, so they'll be up there until I need to change them at some point, which I don't need to often. So yeah, thank you all.